All right, here are the notes for U-Substitution for indefinite integrals. This is section 4.5a. So let's review chain rule for derivatives. So let's say our function is sine of 3x squared. Recall that the rule for chain rule, sine of u, the derivative sine of u becomes cosine of u times u prime. Right? So pretty straightforward as long as we remember to tack on this the inner function's derivative as an attachment. So sine of 3x squared, my u value is 3x squared, so my derivative will simply be cosine of u times u prime, and my derivative of 3x squared will simply be 6x, which I can put in front as a coefficient, so 6x times cosine of 3x squared. All right. So pretty straightforward with applying the chain rule from f of x to f prime. Now we know that derivatives and integrals are inverse operations of each other. So if we go in one direction, we should be able to go back in the other direction. So if I find the integral of 6x cosine of 3x squared, that should bring me back to sine of 3x squared. All right, so I have that here, so sine of 3x squared plus c. All right, we know that this direction works, so the integral of 6x cosine of 3x squared must be equal to sine of 3x squared plus c. Now, we have some problems here just by looking at this because parts of it make sense, right? Integral of cosine becomes sine, and the 3x squared is not going to change. But then, how do we know that we need this 6x in the integral in order for us to produce something that will work, sine of 3x squared? Okay. So that's why we're going to have to go through U-substitution method to ensure that we can keep accountable of terms like this to ensure that we can find the integral appropriately. Okay. We can think of the U-substitution method as the reverse of the chain rule for derivatives. And the idea is that we want to look for the function, a particular function, and for its derivative in the integral problem. Okay. So let me go through the steps. First, we want to assign the u value to the inside function. Usually, we want to start looking inside, looking at the value inside the parentheses. Second, find the derivative for u, but we want to produce some more. Well, the derivative of u is u prime, but rather than writing it as u prime, we want to write it in a more descriptive way. So we want to say du over dx. Okay, so the derivative of u with respect to x, or whatever the independent variable is. Okay. Next step, we solve for dx. Okay. We want to rewrite our integral in terms of u and du, so we're going to go through substitution steps of replacing x and dx in terms of u and du. Okay. And we want to make sure that no x's and dx's remain in the problem. Okay. If there is, then we have to go back and consider that we may have to approach the problem differently, or we may have to take some additional steps so that we can ensure that step 4 passes. Okay. Next step, we should have everything in terms of one variable. We evaluate the integral using the appropriate integral rules. And then finally, we're going to provide our answers in terms of x or in terms of whatever our starting variable is. All right, let's look at example 2. So the indefinite integral of x times x squared plus 1 raised to the 15th. Okay. We want to identify the appropriate u value. So let's say we're going to look inside the parentheses to identify the u value. So our u value, we'll start off by saying is x squared plus 1. Next, we find the derivative of u with respect to x. So x squared becomes 2x, 1 goes to 0. Okay. Cross multiply, so we can begin to solve for dx. So 2x dx equals to u. Divide 2x from both sides, so we get dx is equal to du over 2x. All right. So far we found the derivative of u. We solved for dx. Okay. Next step, we start making our substitutions. Okay. So we look at the original problem here, integral of x. Initially, we don't have anything to replace for x, so we're going to keep it. X squared plus 1 does get replaced in terms of u, so u to the 15th. Okay, so one step at a time, we're going to start replacing x in terms of u. Dx also gets replaced with what we found here. Dx is du over 2x, so we write du over 2x. Okay, so now our next step is see if we can cancel out all the x's, make sure we don't have any x's that remain. So these x's, they do cancel out. One's in the numerator, the other is in the denominator. Okay, and again, we want to make sure that all of our x's cancel out. If not, we need to re-examine our problem. Now, there is a 2 that does not cancel out. All right, but it's okay. It's okay to for us to have remaining constants in our integral. We just cannot have any remaining x's. All right, so we just have to make sure we keep track of our constant. So I'm going to pull this in front. This is du over 2. I can also pull this out as 1/2. This will help me isolate the portions that we still need to continue working on. So the 1/2 will just stay there until we're ready to attach it to whatever our antiderivative is. Okay, so the integral of u to the 15th, simply power rule, so u to the 16th over 16 plus c, multiplied by 1/2, so we get 1 over 32, u to the 16th plus c. And then finally, we want to provide our answers in terms of x, so u gets replaced back in terms of x, so 1 over 32, x squared plus 1 to the 16th plus c. All right, example 3, the integral of x squared secant squared 2x cubed. We want to identify the appropriate u value, so we look inside the parentheses. U is 2x cubed. Derivative, du over dx, power rule, 6x squared. Cross multiply, 6x squared dx equals du. Divide both sides by 6x squared. Dx equals du over 6x squared. Okay. Make our substitutions. X squared does not get replaced, so initially, so we leave that alone. Secant squared 2x cubed does get replaced with u. All right, we found that. And then dx gets replaced with du over 6x squared. Now the x squared will cancel out, leaving us with a 6 in the denominator, which we have to keep track of. It won't cause a problem and preventing us from continuing with the solution, but we do need to keep track of a constant. As long as the variables cancel out, we can we've made the correct u-value substitution. So pull the 6 as 1/6, so we simply have integral of secant squared u du. So we know the integral of secant squared is simply tangent of u. And then finally replace u back in terms of x. So tangent 1/6 tangent 2x cubed.